We're going to start with axiomatic probability from the axioms. So predictions are often probabilities. In particular, suppose we have a variable y associated with a set S of outcomes O1 to OR. For example, flipping a coin, we have outcomes of heads or tails. The value of y is in S, but otherwise we may not know what it is. The value of y may change each time we observe it. A probability distribution is a set of percentages indicating how likely each object in S is to be observed as the value of y. For a fair coin, we have a probability of 1/2 for heads, 1/2 for tails. So heads and tails are equally likely. If we had a loaded coin, 80% chance of heads, then most likely y is heads. Y is heads with 80% confidence is what we'll say. If we have certainty, then definitely y is heads. So given a variable y associated with a set of outcomes S, we often assign numerical labels L, C1 to CR, to the outcomes in S. These are often understood to be class labels. This is where you see them in machine learning. And they're sometimes called tags instead of labels. For example, heads could be 1, tails could be 0. That means we can do math with the labels because they're numbers. If we have a probability distribution, then the percentages indicate how likely each label in L, each number, is to label the value of y. So predicting the label of y, if we have 80% chance of heads, then most likely y is a heads, but we would predict a label of 1. Now in reality, we'd really actually prefer to use vectors. In other words, vector labels. For example, we could label heads 1, 0 and tails 0, 1. So we're looking at probability distributions on a finite set of labels, L equals C1 to Ci up to Cr. A probability distribution on L is any set of non-negative numbers p sub I greater or equal to 0 that sum to 1. P1 added up to Pr is 1. If y is associated with L, then we write P sub I is equal to the probability that y is the label C sub I. This is exactly what we do in machine learning, where a predictive model estimates the probability distribution of a response variable y that's associated with class labels L equals C1 up to Cr for each observation. Often we associate y instead with S equals 1 up to R, the actual index values. Since if we know the index is I, we know the label is C sub I. We also use lowercase y to index S. Sometimes we write P of y is equal to P sub I. This is function notation. And as a result, P of y is P sub y is equal to the probability that y is the probability that the label is C sub I. So the sample space of a process is the set of all possible outcomes of that process. Our focus is on finite but possibly very large sample spaces. If a variable y is associated with S, then lowercase y is used to index S. Of course, that means we have to have an ordering of S to be consistent with our indexing. An event E is just a subset of S. For example, rolling an even number with a 6-sided die is the set E of dice outcomes 2, 4, 6. An outcome is a one-element event, such as rolling a 1. So probability in random variables. Non-numerical outcomes often are assigned numerical tags. We've seen that. But notice that means that we can write our sample space S as T1 to TR, where Tx is a numerical tag of a possibly non-numerical outcome. Tails tagged by 0, heads by 1. Our sample space, therefore, is just 0, 1. Outcomes of an 8-sided die, S is 0, 1, 2, 3, 4, 5, 6, 7. Probability is a function that assigns each event, E, a subset of S, a number between 0 and 1. That means that probabilities are between 0 and 1 inclusive. Variable notation, the probability that X is in the subset E is just the probability of the event E itself. Function notation, P of x, is the probability that x is in the outcome event T sub x, which is the probability that x actually is T sub x. So probability theory is greatly simplified by good notation. So let's look at all this notation again in terms of a random variable x in general. So let's look at probability with a focus on notation. Variable x associated with a sample space of numerical tags, and lowercase x is the index for the variable uppercase x. Probability distribution, a set of numbers, same number of numbers as in S. They're non-negative and they sum to 1. If we have a probability distribution on S, then we say that the P sub x is the probability of T sub x with this notation. And we're using an axiomatic approach, so we're not going to interpret what a probability means at this point. If we have an event, where an event is just a set of outcomes, which we can denote using a permutation of the index set, and we'll use this very handy notation that x in E is used to denote the concept of the outcome indexed by x is in E. So the probability of E, the probability that x is in E, is the sum of the probabilities, where this is over outcomes in E. This is what it looks like with function notation. And using our nice notation, we have a very nice representation. If E is an event, then the probability of E is the sum over x in E of P of x. So we can use variables to explore events. If variable x is associated with a sample space S, there's a probability distribution on S. And if A is a subset of S, then the probability of A is the sum over the x in A's of the probabilities of x. Remember, this is notation. That x in A actually means T sub x is in A. For example, if A is an outcome of a roll of six-sided die being even, then the probability of A is the sum of those probabilities, which is P2 plus P4 plus P6, which is a 6 plus a 6 plus a 6, which is 1/2. We can have set operations. A intersect B is A and B. A union B is A or B. And by A intersect B, we mean a trial or instance of X is in both A and B. Or we can restate that A and B occur jointly in a given trial of X. A union B is when a trial or instance of X is in either A or B. So let's look at some examples. Here's my A and here's my B. The union is just 2, 3, 4, and 6, so each occurring one time. And the intersection is just the outcome 6. Disjoint events are where you have their intersection as the empty set. For example, if we define this new event of just 3, that's not even. A is all even, so their intersection is the empty set. These are disjoint events. A trial of X is therefore in one or the other, but not both, which means that the probability of the union of disjoint events is the sum of the probabilities. This is actually an axiom of probability. So here are the axioms of probability. Given a finite sample space S, a set of numbers, P1 to PR, is a probability distribution on S. If their sum is 1, the P sub j's are non-negative. And for any two subsets whose intersection is empty, in other words, they're disjoint, the probability of the union of those sets is the sum of the probabilities respectively. Everything else can be derived from the axioms, much like we've been doing in this video already. In fact, all probability theory comes from the axioms. Trivially implies the probability of the entire sample space is 1, probability empty set 0. Can prove that if A is a subset of B, then the probability of A is less or equal to the probability of B. Let's just go ahead and do that.
If A and B are subsets of S, then let B not A denote outcomes in B that are not in A. Then A union B not A has to be B, and A intersect B not A is the empty set. So axiom 3 says the probability of B is the probability of A plus the probability of B not A, which is non-negative. And therefore, the probability of B is greater than or equal to the probability of A. We can also define new concepts like conditional probability. So let's first remind ourselves of joint probability. And if we have X associated with the sample space S, then a set B is a condition if X is known or required or constrained to be in B. Conditional probability is the probability of A given the condition B. And we use vertical bars to denote that and place the conditions after that vertical line. Notice that the probability of A and B is less than or equal to the probability of B, so there has to be a k between 0 and 1, such that the probability of A and B is equal to k times the probability of B. But k, therefore, is a probability. In fact, it is the conditional probability of A given B. And that gives us our definition. If A and B are subsets of S, the probability of A and B, the joint probability, is the probability of A given B, the conditional probability, times the probability of B. And if the probability of B is not equal to 0, then it gives us a formula for calculating conditional probability. For example, suppose we uniformly randomly select an automobile from this set X. What's the probability that it is a truck given that it is red? Well, we can just use the concept of conditional probability. The condition the vehicle is red means we can ignore all the non-red automobiles. 3 of the 5 red vehicles that remain are trucks, and therefore the probability of a truck given that the vehicle is red is 3/5, or 0.6. So let's do this from the formula. Our condition is that B is a red vehicle. Our A is that the vehicle is a truck. Their intersection is that the vehicle is a red truck. The probability of a vehicle being a red truck, there are 3 of those out of the 10 total. And the probability of a red vehicle, there are 5 red vehicles out of the 10, so that's 1/2. So the probability that we have a truck, given that the vehicle is red, is the joint probability over the probability of B, which is 3/10 over 1/2, which is 3/5, which is 0.6. So conditional probability allows us to define the concept of independent events. Here is our definition of conditional probability. And if the probability of A conditioned upon B is just the probability of A, then we say A is independent of B. In other words, the probability of A if B occurs is the same as the probability of A if B does not occur. For example, suppose me and a Dr. Yu in China on opposite sides of the earth, therefore independently, flip fair coins. A is the event of a heads for me, and B is the event of a tails for you. The probability of B conditioned upon A for Dr. Yu is 1/2, regardless of whatever coin toss I had. Similarly, the probability of A given B is just the probability of A is 1/2 independent of Dr. Yu's outcome. Probability of A given B is the probability of A implies that the probability of A intersect B, the joint probability, is the product of the probabilities of A and B respectively. The probability of heads for me and tails for you is the probability of heads for me times the probability of tails for you, 1/2 times 1/2, which is 1/4. The probability of A intersect B is the product of the probabilities, but it's also the probability of B intersect A, which means we also get probability of B given A as the probability of A. In other words, A is independent of B only if B is independent of A. And note that independence of subsets is actually a property of the probability distribution that is applied to our sample space. For example, the event A equals vehicle is a car is independent of the event B equals vehicle is blue, because there's one blue car and one blue truck. So let's look at this. A is vehicle is car. B is vehicle is blue. A intersect B is vehicle is blue car. And there's exactly one blue car out of the 10 possible. The probability of A, we have a car, is 5 out of 10, which is a half. The probability of B is 2 out of 10, which is a fifth. 1/2 times 1/5 is 1/10. Therefore, the probability of A intersect B is the probability of A times the probability of B. A and B are independent events. Remember, all probability theory comes from the axioms. We just use axioms to derive conditional probability, for example. And later, we can use the fact that A intersect B is B intersect A to show that we get the probability of A conditioned upon B times probability of B is the probability of B conditioned upon A times probability of A. And rearrange that, we end up with what's known as Bayes' theorem, which we will use later. Well, what about the law of large numbers, you might ask? Can derive it from the axioms. What about probability as a limit of relative frequency? Can derive that from the axioms also. All we need are the probability axioms and good notation, which always simplifies and clarifies the study and application of probability.